So the second experiment in our Swansea Analyst contest for this year is all about aspirin analysis by spectroscopy. The actual experimental part of this is dead easy. It's the calculation part that can take some time, and also it's worth spending a little bit of time introducing the background for it. Anyway, what we're going to be doing is we're going to be looking at a coloured substance. Why are things coloured? It's because they absorb particular wavelengths of visible light and allow other wavelengths to pass through or to be transmitted. The more intensely coloured things absorb more light, and the way we say that in a fancy fashion is we say they've got a higher absorbance, A, they absorb more light. And for dilute solutions, the absorbance A is directly related to the concentration, it's proportional to the concentration as described in Beer's law. A, that's the absorbance, is equal to epsilon L. Now these are just constants that are associated with a particular substance, that's the epsilon, and L is how much of the substance, the path length you had there. So these are going to be a constant throughout our experiment, okay? And then here's C, the concentration. So you can see A, absorbance, is equal to a constant times the concentration. And that's so important, absorbance directly proportional to the concentration. I think I've said that one way or another 5 times. This Beer's law is the fundamental idea that we're going to be utilizing in this experiment. So we can determine the concentration of a coloured substance if we can measure the absorbance of that solution and we know the values of epsilon L. And to do that, we use an instrument called a spectrophotometer. Spectrophotometer shines light through a sample of different wavelengths of light and compares the intensity of the light after it's gone through the sample with the intensity before. Okay, and we can study these coloured compounds by determining how much light is absorbed by known concentrations. So if we measure the absorbance and we know the concentrations, now we can determine epsilon L. And then once we know epsilon L, we can measure the absorbance of an unknown sample to determine the concentration. And that in a nutshell is what we're going to do today. If you're in the lab, you would see our spectrophotometer. It's a nice diddy little thing there. We put our sample in a square test tube called a cuvette into that hole there, and then we beam light through it. So the light goes in there through the sample. We measure what comes out afterwards, and then we'll display the results on our computer screen. So here is a sample in the cuvette, and you can see it's lit up because the light is passing through there. And again, light passes through, some of it's absorbed, the rest is transmitted. Knowing what goes in, measuring what comes out, enables the computer to plot out the absorbance, and we'll get something like this. Okay, along the bottom there is wavelength of the different types of visible light. We got this pretty little background that shows you that the shorter wavelength or the higher energy visible light is purple, and then of course you get that famous little sequence going through violet or purple, then blue, and then green, then yellow, then orange, and then red. And this of course is the longer wavelength or the lower energy of the visible spectrum. Absorbance up here. So what we see is that the sample isn't absorbing much of the red, absorbs a little bit in the higher wavelengths red, a little bit of the orange, peaks in the green spectrum, okay, and then goes back down, isn't absorbing as much here, absorbs a little bit up in the purple as well. So this is the absorption spectrum of whatever my sample is in here, and the computer prints out, I didn't put everything on there, but essentially these are the absorbance heights that match up to the particular wavelengths that's off the screen there. So this is the spectrophotometer we're going to use, and this is the kind of output that we get. Now in this particular lab, we're going to measure the concentrations of ferric salicylate. Try saying that 5 times quickly, which is a lovely purple color. So what we're going to do, take different concentrations of that, measure the absorbance, and we'll use Beer's law, measuring the absorbance for the known concentrations. We can calculate epsilon L. Okay, then we're going to take an unknown solution of the ferric salicylate, measure its absorbance, and thus determine its concentration, because if we know epsilon L, measure A, we can calculate C. Now this is a particularly useful little process because it's actually used to test for aspirin. Okay, ferric salicylate of interest for a test for aspirin. Let's actually look at the chemistry associated with this. I'm going to start with the compound salicylic acid. That's what we're going to use in the lab. We're going to measure out a certain amount of salicylic acid. We're going to put it in solution. We're going to react it with sodium hydroxide to make this compound sodium salicylate. So you can see all that's happened is the Na has replaced the H there. Now, if we take sodium salicylate and we react it up with Fe3+, we make this beautiful purple compound here, ferric salicylate or iron 3 salicylate, in which there's the Fe3+, and it's reacted with 3 of these formerly salicylic acid moieties. Essentially, the Fe3+ has replaced the Na+ on 3 of these. Okay, so this is the reaction we'd actually do in the first part. We take known amounts of salicylic acid, react it up with sodium hydroxide to get known amounts of sodium salicylate, which we then turn into this pretty purple compound to do the analysis. Now, I said that was something to do with aspirin, didn't I? Well, this is aspirin here. It is salicylic acid. There's the benzene ring with the acid group, but instead of an OH there, instead of that so-called phenol group, if you know that, we've put on this acetyl group here. Okay, so acetyl salicylic acid, this compound here is aspirin, give you the molar mass as well. Well, if we take aspirin and we dissolve it up in a solution of sodium hydroxide, the aspirin converts to the sodium salicylate again. In other words, you break off this group here and replace it effectively with the H, and we replace the H on this acid group with the Na. And so we take aspirin, we turn it into sodium salicylate, we convert that to the ferric salicylate, and we can determine the concentration of the sodium salicylate and hence the amount of aspirin, very much similar to what we did if we just started with salicylic acid. So we're going to use salicylic acid to develop all our known values, our epsilon L, and then we're going to take some unknown aspirin, going again through sodium salicylate to determine how much aspirin we have in there. Hopefully that vaguely made sense. As we go through, anything that's unclear might become clearer if we're lucky. So, first part, I'm going to take known concentrations of sodium salicylate made from salicylic acid, reacting with Fe3+, and then we're going to make the aspirin solution from a tablet, measure its absorbance, get the concentration of the sodium salicylate, and hence the mass of the aspirin. The method. Measure out 25 cubic centimeters sodium hydroxide in a 250 cubic centimeter volumetric flask. This doesn't have to be too precise. Then we're going to weigh out about 300 milligrams of salicylic acid and put it into the flask, recording the exact mass that we use. And then we're putting the stopper on the flask and swirling it. So because we got salicylic acid, we got sodium hydroxide. As we do that swirling, the salicylic acid is making the sodium salicylate. Want some data? Here is the mass of my weighing boat here. I'm then going to weigh out or fill that, not fill it, but put some salicylic acid in there. There's the white powder of salicylic acid, and here is the new mass. Okay, so you need to know the mass of the salicylic acid if you're going to continue on with this. So now we've got this in a 250 ml volumetric flask. So we're going to add enough water up to the line on the flask. There's the line right there, if you can see it, and there's the water. So we've now made a solution that came from essentially 300 milligrams of salicylic acid converted to sodium salicylate, right, in 250 cubic centimeters, or of course we usually talk about concentration in terms of in cubic decimeters or liters, so 250 cubic centimeters in a liter. So we got about 300 milligrams salicylic acid converted, or 1200 milligrams of the salicylic acid converted to the sodium salicylate. Now at this point it's worthwhile, first of all, you doing some calculations to keep track of things, and also because sometimes these calculations can run together, I'm going to give you some examples of them. So the first thing you need to know is you weighed out the salicylic acid. How many moles of that did you get? Well, I'm going to pretend that I weighed out exactly 0.300 grams. The amount I actually weighed out, of course, you can get from those the pictures of the balances on the previous slide. So the moles is going to be the 0.300 grams. divided by the molar mass of salicylic acid, because that's what I weighed out, 138.1 grams per mole. So I got 2.17 times 10 to the minus 3 moles of salicylic acid. Then I dissolved that up and reacted up with sodium hydroxide. And 1 salicylic acid makes 1 sodium salicylate. So therefore, I've got 2.17 times 10 to the minus 3 moles of sodium salicylate in here. Okay, and so what's the concentration of that sodium salicylate in moles per cubic decimeter? Well, it's equal to the 2.17 times 10 to the minus 3 moles of sodium salicylate that I've just determined was in there, divided by, well, it's 250 cubic centimeters, so 0.250 cubic decimeters. So the concentration of my solution, my stock solution as we call it, of sodium salicylate is 8.69 times 10 to the minus 3 moles per cubic decimeter. And we'll bring this number back in later on. Okay, so I'm starting with that concentration of my sodium salicylate. So now what I'm going to do is I'm going to dilute that sodium salicylate and add the Fe3 plus solution, otherwise known as Trinder reagent. It's Fe3 plus compound mixed with concentrated HCl, and I'm going to measure the absorbance of each of these solutions. Okay, so the solutions I'm going to make are this: 0.5, 1, 1.52, 2.5, so different amounts of the sodium salicylate solution, enough water to take that total volume up to 2.5, so 0.5 of this plus 2 of that, all the way to 2.5 of the sodium salicylate, so I don't need any more water, and in consistently adding the same amount of the Trinder reagent. Okay, now what I'm going to do throughout is I'm just going to say, well, I'm adding that Trinder reagent just to make it colored, but the important concentration throughout is going to be the concentration of the sodium salicylate. Okay, so that's what I'm going to imagine I'm going to be measuring, and you can see that as I go from here to here to here to here to here, the amount of the sodium salicylate goes up by 2, then by 3, then by 4, then by 5. So I've got increasing concentrations of the sodium salicylate. Now, when I add the Trinder reagent, it makes it purple, and you can actually see those different concentrations by the extent of the purple color on this slide here. So this was solution 1 all the way up to 5. You can sometimes see things a little bit better from top or the side. You can certainly see, I hope, that as I go 1, 2, 3, 4, 5, my solutions are becoming more intensely purple because I have more sodium salicylate that's reacting with the iron in each of those. Continuing on, pipette or pour some of the solution in a cuvette, put the cuvette in the spectrophotometer holder. There's the cuvette with one of those pretty little purple solutions in it. And then I get a spectrum that's just like this one. It's actually very similar to the one I showed as my example earlier on. A little bit of absorbance going on here in the purple, but the predominant absorption, the big peak, this is the one I'm going to use, is in the green spectrum, coming up with a peak at around here, which is about 535, between 530, 540 nanometers. Now I do that and I record the maximum absorbance from these numbers over here. Okay, so blowing them up nice and large. Here's my peak spectrum. We said it was about between 530 and 540. These are the nanometers that I'd be reading. Here is the maximum absorbance. You can see the maximum absorbance here, 1.077 at about 528 nanometers right there. So I would record in this case that the absorbance 1.077. So anyway, I've got 5 solutions, so I'm going to take the spectra of all 5 solutions and I put them all on the same screen, and this is what it looks like. Obviously, this is the least concentrated because it absorbs the least. Then you can see this is about twice as much, almost 3 times as much as that one, 4 times as much as the original, 5 times as much of the original. Okay, getting more close at it. This is solution 5. That was the most concentrated one. The absorbance 1.225. There's 4.995. Solution 3, 0.657. Solution 2, 0.495. And solution 1, 0.246. So there's my absorbances for those 5 solutions that I made up. Now that's it for the actual methodology. Now we need to do calculations. So here were the solutions I made up. If you remember, in each case I had a total volume of 12.5 for my different solutions, and what was different between them, same amount of the Trinder, the colouring agent, what was different between them was the amount of the sodium salicylate that I put in there. And I've just measured the absorbance for those, so now what I need to do is calculate the concentration of each of those solutions. Okay, and again, I'm going to be focusing on talking about the concentration of the sodium salicylate, just thinking of the purple color as being the coloring agent that I'm putting in. Okay, now you need to think about two things. First is, what was the starting concentration of this in moles per cubic decimeter? And remember your dilution equation, C1V1 equals C2V2. And I'm going to go back and use my original one. Remember, this was my play concentration of the sodium salicylate. So I took 0.5 cubic centimeters of that sodium salicylate. There's 8.69 times 10 to the minus 3 moles per cubic decimeter. And then I added enough other stuff, water and Trinder reagent, to make the total volume 12.5. Okay, so now I can calculate that new concentration, that new diluted concentration, which is what I'll pop in here. So you need to use your concentration, right, and do that calculation 5 times. So now we're going to pretend that this column is filled with the concentrations that you've calculated simply by using C1V1 equals C2V2. At this point, we're going to go back to Beer's law. The absorbance is epsilon L times the concentration. We've measured the absorbance for each concentration, therefore we can calculate epsilon L. And there's two ways you can do this. You can do it algebraically. You can say, well, I've got my absorption for 1, 2, 3, 4, 5. I calculated the concentration for each of those. And so for each of those pairs of data, I put in the absorbance, concentration, calculate epsilon L. For this one here, absorbance 0.495, concentration, whatever you determine this to be, get epsilon L. So you can get 5 different values of epsilon L and then get the average value that you can use for the second part of the experiment, the unknown determination. The nicer way to do it, however, is graphically, because let's look at this relationship here. Absorbance is proportional to concentration. So if I plot out a graph of concentration C along the x-axis and absorbance on the y-axis, my data should have a nice straight line. Okay, and by the way, because absorbance is directly proportional to concentration, if you have 0 concentration, you shouldn't have any absorption. You can put in the origin, plot the best straight line through that, and the slope of that line should be epsilon L. Okay, absorbance is constant epsilon L times the concentration. The value of that constant is the slope of the graph. So again, if you want to do it graphically, plot your graph out, measure the slope, and of course you can do this in Excel if you know how, and get your value of epsilon L. So either algebraically or graphically, now you know epsilon L for our pretty purple substance. So now let's get to the point of this in terms of proper life, and let's go ahead and analyze some aspirin. So I went to a store to buy some aspirin. I'm not going to tell you which one. There's no product placement going on here. But anyway, I took one of those tablets. I crunched it up. I treated it as in the original steps 1 to 3. So in other words, I put all the aspirin in it. I dissolved up as much as I could, put in some sodium hydroxide to get up, and added enough water to add to 250 cubic centimeters. Filtered out because there's always a little bit of filler there, and then make the solution up to 250 cubic centimeters. So now I have a 250 cubic centimeter solution that contains all of the aspirin that got converted to sodium salicylate from my tablet. I then took 2.5 cubic centimeters of that solution, mixed it with the 10 cubic centimeters of Trinder reagent. So again, 2.5 plus 10 is the 12.5 cubic centimeters of solution. Then I measured the absorbance 3 times for that, and then I did 2 more tablets. So there we are, first tablet, second tablet, third tablet. There's the absorption for each one measured out 3 times. Okay, obviously there shouldn't be any difference, and you can see they're pretty close to each other. And now we can use these data to finish off. So again, calculations. I'm going to give you a link for the data sheet to which you upload your answers to these calculations. So first was, what was the average absorbance of the unknown? On the previous slide, you had 9 values. What was the average? Now, you calculated epsilon L. You either did it algebraically or you did it graphically. It's the same epsilon L because it's the same purple color that comes from the Trinder reagent with sodium salicylate. So you can just use that epsilon L with the absorbance of the unknown to get the concentration of the unknown solution. And that's the concentration of the unknown solution in terms of sodium salicylate. Okay, now of course that concentration was diluted, so now you need to work backwards to get to the concentration in the original 250 cubic centimeters. Once you got the concentration of aspirin in that 250 cubic centimeters, you can get the mass of the aspirin in that 250 cubic centimeters. And if the tablet, each tablet weighed about 100 milligrams, what was the percentage of aspirin in those tablets? Do those calculations, pop your answers into my online answer sheet. Again, if you're given the PowerPoint that accompanies this video, you can just click on the live link. Alternatively, the link has been sent to your teacher. So a little bit more complicated. Hopefully you followed it, because what we did here is what people do around the world in pharmaceutical labs or generally analytical chemistry labs, using spectroscopy to determine how much of a particular substance you have. Anyway, as I said in the previous one, hopefully I will get to see you all in 3 dimensions coming to do some experiments in our lab. Do hope you enjoyed this. Goodbye.